In the previous video, we talked about DC resistance circuits and how we can use Ohm's power law to calculate power in a DC resistance circuit. If you know the voltage across the resistance and the resistance of the resistor, you will be able to use the formula V square divided by R to calculate the power. If not, if you know the current flowing through the resistor and the resistance of the resistor, you can multiply I square, the current square, times the resistance to calculate the power. So that's Ohm's power law. And how do we find power in a alternating current resistance circuit? So here is a alternating current source and you have a resistor. So in this case, since the resistance is going to be some constant value, when the voltage increases, the voltage and current is going to be proportional. Proportionally, the current will also increase. So when the voltage is negative, the current will also be negative. For our power calculation, we just multiply our voltage by the current. So during the positive half cycle, so the current is positive and the voltage is positive, so the power is going to be positive. Likewise, in the negative half cycle, both of them are negative. So the current is negative and the voltage is negative. And if you multiply, say, -1 times -1 is +1. So it is going to be positive as well, which means when the load is, or when a load is resistive in nature, the power is always flowing from the source to the load. Okay, so the calculation doesn't change much in terms of how the power is calculated. So the power, so we'll talk about reactive power in a while. The real power is going to be the total power that is consumed by the resistor, so which you get by multiplying the voltage and current. So if you multiply those, you will get the power, like same as a DC circuit. But here we have other powers, like let's see what those are. So in a alternating current circuit, if the load is not just resistive, there are two other types of load, which we will see in the next slide. But if there are other types of loads here, they produce their own magnetic field and electric field. So usually in a circuit, the source is the one that delivers power to the load. But when the load is either resistive, or sorry, not resistive, if the load is either inductive or capacitive, they store energy and they send back the power to the source. And this is a power that is oscillating back and forth from the source to the load and load to the source. And this power is called the reactive power. So real power, we call it real power because this is the real work that is done by the component. So let's say an electric bulb, so it will have a resistance. It will not have the magnetic component or the capacitive component. When I say magnetic, I'm saying the inductive or the capacitive component in it. So it will be just resistive. So whatever power we deliver to the light bulb will be converted into light. Not all light, but like maybe there might be some heat involved. If it was a heater, everything will be converted into heat. Likewise, for any useful conversion, or like say any power that is real is the one which will be converted into some useful work. This reactive power just goes back and forth, and this is not doing any useful work. And there is another power called apparent power, which is just the sum of the reactive power and the real power. That is the total power in the circuit. So this is what you will have to know to understand the resistance, an AC resistance circuit. There are two other loads which I'm going to give you for an information. And towards the end, like, we will see how we'll collect or like how to calculate the powers from a question by solving few examples. And the information I'm going to share next about inductive and capacitive is important. If you have more questions, we can discuss that during one of our sessions. And if not, like, you will not actually, like, say, receiving more questions on the inductive and capacitive part of this module. So let's discuss three different types of loads. But again, you can expect questions from the resistive type loads. So these are the three types of loads. So as I said, the resistor load, it doesn't make any difference. It doesn't store any charge and like delivers back always the current flows or like the power flows from the source to the load. And there are two other types. One is capacitive. So here the capacitor generates an electric field, and this capacitor will store some energy, and it'll send back the energy to the source, and this oscillation causes the reactive power. Likewise, the magnetic field will store some energy, and then during the other half cycle, it will send back the energy to the source. So this is the capacitor and inductor. So if you apply a DC voltage to this circuit with a capacitor and inductor, it will behave differently. So this will be an open circuit. No current will flow through this because this is a this one has a dielectric material, so there is no conductor involved here, so it is an insulator, so the current doesn't flow through this. And here there is no magnetic field, because for the magnetic field to be produced we need an alternating current. If it was a direct current, so it will just be a wire, that's it. So it will have some resistance maybe, but like it will not produce any magnetic field. So these are the two types of load. And let's see some animations. So this is what we calculated. So when the current is positive and when the current is negative, so this is the resistive load. So the power always flows from the source to the load. But in the other situation, so inductor and capacitive loads, so in an inductor load, this is the voltage and the current kind of, so this is, sorry, this is the capacitive, my apologies, just give me a second. So the current lags the voltage, and then the power like kind of oscillates back and forth. So this power is not being used for any useful purposes. So this is all reactive power, no real power at all. So the same thing applies for this one as well. The current lags, and the current leads. So what happens here is, again, the power oscillates back and forth. So there's no useful work done here as well. And this is some practical, So here we have some practical load. So let's say you have a motor. And again, like, you don't have to worry about this much. You are paying Nova Scotia Power just by watts, the real power you actually consume. But like, say if there was an industry that is a high power consumer, so they would be paying for the reactive power as well. So as a residential customer, you don't have to worry about this one. But if there is a motor, it'll have it'll be something like that. It'll be like 30%, 30-degree lagging. So that 30-degree lag of current will produce, say, this is the actual power graph. And if you see, there is a small power that oscillates back and forth. And this is the power that is being wasted. And the majority of this power is real power, and like that real power is what is converted into useful work. Say a motor that might be used for pumping motor, like for the pumping action, that's where this power is being used. But like this reactive power is just oscillating back and forth, and it is not being used for anything. So that is alternating current circuit. Again, like you don't have to know much about, like, you don't have to get into nitty-gritty things of inductor and capacitive loads, but we are just going to use them for calculating power, and that will be very useful for you later on. So how do we calculate power in an alternating current circuit? So for calculating the active power, you need to know this is the power factor. So when we say the current leads or lags, so that this is the phase angle, like which we talk about. So cos phi. For most of the problems, we give you the value of cos phi, the power factor, and if not, the angle will be given. So you can use to calculate that and multiply that with the power to calculate the active power. So let's say if it was like 0.7 power factor, if the active power was 100, or like say if the current was voltage was 10 volts and the current was 1 ampere, and if the power factor was 0.75, so only 75% of the total power that is consumed, the apparent power, like that is the total power, that is like including the active and reactive power. So almost 75% of it, only 75% of it is like converted into real work. And the remainder of the 25% is the reactive power, which just oscillates back and forth. So these are the three powers. So if you just multiply the VRMS and IRMS, you will get the apparent power. And if it was a resistive load, so the power factor is going to be 1, which means everything is active power. So at that point of time, active power is going to be equal to the apparent power, and reactive power is going to be equal to 0. So these are the formulas that you will use for calculation. So let's do a small example, and then you will understand like how this works. So here, an industrial motor has a nameplate that reads 210 volts, 60 hertz. So this should be North America. So 60 hertz power supply and 12 kilovolt amperes. So this is the apparent power. So this is the multiplication, or this is the product of IRMS times VRMS, and 0.78 power factor lagging. So the apparent power is 12 kilovolt amperes. So that is the apparent power. And the active power, you just multiply that with the power factor lagging, and then you get 9.36 watts. And for reactive power, you have to calculate phi. So cos phi is 0.78. So we take the cos inverse, so we get phi. And that phi is substituted here, so sin phi. So you have a value for that. You just multiply that by 12 kilowatt amperes, and that is going to be 7.51 kilowatt. So that is, my apologies, there's a small issue here. So this will be kilowatts, not just watts. It's going to be kilowatts here. So that is an example. So the problems would be very similar to this. We'll not be digging deep into the inductive and capacitive loads, how there are other things called impedance and things like that. We'll not be getting into that. That'll be too much for this course. That'll be out of scope for this course. But it is better for you to understand the power calculations. So there is an assignment question here. So question 12, a factory has the following 4 major loads. A motor rated at 5 horsepower. So again, we use horsepower for motors. So 1 horsepower is like 0.7457 kilowatts and 0.8 power factor lagging. So you know how to calculate the active power. So you just multiply that, and you have the power factor. You just have to multiply that as well, and then like calculate that power. And you have a heater rated for 1.2 kilowatt, 1 power factor. So 1 power factor means all the heater. So heater is a resistive load. So everything is converted into real power. So that is 1.2 kilowatt. And you have 10 times, so make sure you multiply that by 10, and you have 120 watts. So this is also a resistive load. And how will you convert? So 10 times 120, you get the power that is required by this 10 light bulbs. So you just add these 3 together. The active power, the only place we need to calculate the active power carefully is here. You just have to multiply 5 times this value, so that will give you in kilowatts, and then multiply that by 0.8 to get the active power for the motor. And so the reminder power is for reactive power. So you just add all 3 and the active portion of this, and both of these are only consuming active power. You add all 3 and then you get the total active power. And for the reactive power, so light bulb is a resistive load, no reactive power. Heater is a resistive load, no reactive power. But this one is not, so there is going to be some reactive power. So you just multiply the 5 HP converted into kilowatts hour, and then sine of cos inverse of 0.8. So that is going to be your reactive power, and like we don't have any other reactive power, so just you add that, and that'll be the total reactive power. So that is question 12. It should be easy, simple, and in the next session we will talk about energy, and that should conclude module 1.